So far, we've only been working with single tasks. But where the task parallel library really shines is in weaving together hundreds or thousands of tasks in complex patterns. To connect tasks together, you basically have two dimensions to work with. You can create a hierarchical layering of tasks and have parent tasks break down complex work into asynchronous units of work that can run in parallel. The parent tasks can then assign these units to child tasks. Once all children have completed their work, the parent tasks aggregates the results and continues. The other dimension is sequential. Not all complex tasks can be broken down into independent components. Sometimes, a task consists of a discrete number of steps that have to be performed in a specific order. For this scenario, you can link tasks together into so-called continuations, sequences of tasks that execute one after another. You can freely mix and match from both dimensions. A parent task could assign work to 3 child tasks, wait until they complete, and then move on to the next task in a continuation sequence. In this lecture, we are going to look at the first dimension, the hierarchy of parent and child tasks. So how does this hierarchy work? Well, let me show you another diagram. Here we have a parent task that is working on some kind of complex operation. The work can be split up into 3 asynchronous units of work that can execute in parallel. So the task starts 3 child tasks and assigns 1 unit to each of them. Now here's the thing. The parent task will not complete until the final child task completes. So if you are waiting for the parent task to complete, you are also automatically waiting for all child tasks. Another cool feature is exception and cancellation handling. If a child task gets cancelled, the task cancelled exception will bubble up to the parent task and get rethrown in the calling code, either at the wait method or in the result property. The same applies to exceptions. Any exception thrown by a child task bubbles up to the parent and gets rethrown. Now you might be thinking, aha, but what happens when more than one child task throws an exception? And this brings me to another nice feature of tasks. They always wrap exceptions in an aggregate exception. So if all 3 child tasks fail, the 3 exceptions get wrapped up in a single aggregate exception, and that exception is rethrown at the wait method or the result property. Okay, it's time for some code. I am going to write a simple application to demonstrate parent-child tasks. Let's do something really simple. I am going to write a program that takes a line of text and then it reverses the characters in each word. Finally, it joins the reversed words back together in a sentence. The reversing of characters in a word is a step we can assign to child tasks. For each word in the sentence, I will create and run a new task and have that task reverse that single word. Finally, the parent task will gather up all the results and reassemble the sentence. Let's go through the code line by line. At the top here is a generic list of tasks that return a string. I will use this list to store my child tasks, so that I access them from the main program method. Next is a simple string reversal method called reverse string. You can see that I loop through all the characters of the input string in reverse order, append them to a string builder, and return the reversed string. But here is a line I'd like to direct your attention to. The reverse string method first goes to sleep for 1 second, and then it starts reversing the string. So, for a 10-word sentence, I would expect a total runtime of 10 seconds. Now let me show you the main program method down here. I start with this hard-coded sentence. The quick brown fox jumped over the lazy dog. Now remember, the reverse string method takes 1 second to process each word, and this sentence has 9 words in it. So I expect a total runtime of at least 9 seconds. Next, I run a new task that calls the process sentence method to work on the sentence. Note the call to wait here at the end. So, this method will block until the parent task has completed. And there's also a stopwatch here that measures the total runtime of the parent task in milliseconds. So, after having waited for the parent task to complete, I loop through the generic task collection and display each word. This will display the sentence with the characters in each word reversed. Okay, so all the magic happens in the process sentence method. Let's take a look. This for each loop here splits the sentence into individual words and loops through them. For each word, I start a new string task that returns the reversed words plus a trailing space as a result. Now, normally when you start a task inside another running task, you simply create an unconnected task that runs on its own. But when I provide this setting here, task creation options dot attach to parent, then the new task will be a child of the running parent task. And remember, parent tasks will only complete after all of their child tasks have completed. So this setting extends the runtime of the parent task until every child has finished reversing their word. You'll also notice this other setting here, long running. This forces the task scheduler to assign a new thread to each task, instead of using the thread pool to execute the tasks. I do this because my tasks take 1 second to complete, and therefore I consider them to be long-running. Okay, let's run the program and see what happens. Here we go. I'm running now. And here are the results. The parent task took slightly over 1 second to produce the reversed string. This proves that each child task ran on a separate thread. Consider, there are 9 words in the sentence, and each reverse string method takes 1 second to complete. The only way to reverse the entire sentence in 1 second is by using 9 threads. The parent-child hierarchy ensured that the parent task can only complete when all child tasks have completed. So in my main program method, right after the wait statement, I know for sure that at this point in my code, all child tasks have completed. To prove this to you, I'll add some more code. Here is a loop that goes through all child tasks and displays their completion status. I execute this loop right after waiting on the parent. So, I expect each child task in the collection to display true, because the parent can only complete after all child tasks have completed. Let me run the program again. And there's our proof. There is a 1 second delay, and then the parent task completes. At this point, all child tasks have also completed. Now watch what happens when I remove the Attach to Parent option. I'll replace it with a None. So now the child tasks are completely unconnected to the parent. The parent will now complete immediately after it has started the 9 child tasks, without waiting for them to complete. I'll run the program again. Here we go. And now you see completely different behavior. The parent completes immediately after much less than a second. All child tasks are still running at this point. But when I try to gather the results of the child tasks, you can see that the program blocks for a second. These are the 9 result properties that are blocking because their child tasks are still running. Okay, so what have we learned in this lecture? Tasks can be connected hierarchically and sequentially. Hierarchical tasks are called parent and child tasks. A parent task will not complete until all its child tasks have completed. Exceptions and cancellations bubble up from child tasks and are wrapped in an aggregate exception in the parent task.